Hello, welcome to the second International Conference on Functional Materials and Civil Engineering, and thank you for participating in this conference. My name is Ömer Burak İstanbullu, and I am an assistant professor at Department of Biomedical Engineering in Eskişehir Osmangazi University in Turkey. My presentation is going to be about next generation implants, combining 3D printing with advanced biomaterials for superior mechanical properties. I provided the outline of my presentation in here. At first, we will begin by introducing biomaterials and their medical applications. Next, the key characteristics that make these materials ideal for implants will be explored. We will then discuss how integrating 3D printing with biomaterials is advancing medical devices. This includes examining 3D printable biomaterials, their properties, and a case study on enhancing polylactic acid and polycaprolactone with microparticle reinforcement. A comparison of 3D printed implants with traditional designs and the challenges faced in 3D printing biomaterials will also be addressed. Finally, we will look at future trends and wrap up with a summary of key points. Biomaterials are non-viable biocompatible materials used in medical devices or implants to interact safely with biological tissues. They are classified into several categories based on their composition. Metals and alloys such as titanium alloys, 316, stainless steel, cobalt chromium alloys, and tantalum-based alloys. Ceramics including alumina, zirconia, bioglass, and hydroxyapatite. Polymers of ultra-high molecular weight polyethylene, polytetrafluoroethylene, polymethyl metabolite, and polylactic acid. Additionally, the composites, which are the combination of different materials like carbon fiber reinforced polymers and glass reinforced polymers. On the right side of the slide, you can see a diagram highlighting the various implantable medical devices like cochlear implants, dental implants, cardiovascular implants such as pacemaker, and prosthetic joints. The choice of biomaterial depends on the mechanical properties, biocompatibility, and the integration with biological tissues. Ongoing research aims to create more effective and personalized implantable biomaterials. Biomaterials must meet physical, chemical, and biological requirements to be suitable for medical applications. Physical requirements including mechanical strength, flexibility, and hardness. The mechanical strength is essential for load-bearing applications like bone implants and joint replacements. Flexibility is necessary for soft tissue applications such as cardiovascular stents or certain prostheses allowing the material to conform to body movements. The hardness is also important for hard tissue applications like dental implants or orthopedic screws, providing structural support and durability. On the other hand, chemical and biological requirements include biocompatibility, which means the material shouldn't provoke an immune response or cause adverse reactions. Hemocompatibility, which is crucial for devices in contact with blood, like heart valves or vascular grafts, to prevent clotting or blood-related issues. The biomaterial must also be inert so they do not react with bodily fluids or tissues, ensuring the stability. Additionally, the material shouldn't release any toxic substances that could harm the body. Understanding the characteristics of various biomaterials used in medical implants helps us appreciate their applications and the limitations. Metals and metal alloys, such as gold, platinum, titanium, and steel, offer high material strengths and they are easy to fabricate and sterilize. These makes them ideal for orthopedic implants, screws, pins, or plates. However, they come with some drawbacks, such as being corrosive and having an excessive elastic modulus, which can lead to implant failure and loosening. Ceramics and carbon compounds, like calcium phosphate salts, glass, and oxides of aluminum and titanium, are known for their high material strength and biocompatibility. Their resistance to the corrosion makes them suitable for bioactive orthopedic implants and dental implants. The main challenges with ceramics are their difficulty in molding and excessive elastic modulus. The polymers, including PMMA or PCl and PLA, are advantageous due to their biodegradability and biocompatibility features. They are easily moldable and readily available, providing them to be directly utilized in tissue engineering scaffolds and drug delivery systems. However, polymers can be leachable in body fluids, hard to sterilize, and possess low mechanical strengths. Composites, such as dental filling composites and carbon fiber reinforced metal metacrillate form cements, exhibit excellent mechanical properties and corrosion resistance. They are used in porous orthopedic implants or dental fillings. Despite their superior properties over other materials, composites can be expensive and require laborious manufacturing methods. 3D printing, which is an additive manufacturing process, builds objects layer by layer. The main types of 3D printing technologies are fused deposition modeling, selective laser sintering, and stereolithography. The FDM-based production utilizes various materials with melting points below generally 300 Celsius degrees. In this technique, polymers like PLA, PGA, ABS, PCl, and TPU, or composite materials enhanced with nano or microparticles for improved mechanical properties, are utilized for production of 3D objects. Process steps for creating a 3D object by 3D printing includes the 3D CAD modeling, which is digital design of the object, then conversion of the 3D model to STL by means stereolithography file, which describes the surface geometry for 3D printing. Then the slicing software slices the model into thin horizontal layers and generates the tool path for the printer, determining how each layer will be printed. The tool path information is then fed to the 3D printer by a generated G-code. The printer follows this path considering the specific G-code, including the printing parameters such as printing temperature and speed or layer deposition thickness to deposit the material layer by layer, gradually building up the object at the final step. The 3D printer executes the instructions from the slicing software, extruding material through the nozzle. The final product is a 3D dimensional object that accurately replicates the digital 3D CAD model, ready for use in medical applications. 3D printing combined with advanced biomaterials is revolutionizing medical technology in prosthetics, implants, surgical guides, and bioprinting. 3D printing allows us to produce customizable, cost-effective, and lightweight prosthetic solutions tailored for amputees. This technology enables the creation of prosthetics that perfectly fit the unique anatomy of each patient, enhancing comfort and functionality. Implants can be personalized to match the exact shape and size needed and improved fit and function for each patient. 3D printed surgical guides are precise, patient-specific tools that enhance the surgical accuracy. These guides enhance surgical accuracy, reduce errors, and improve patient outcomes. One of the most exciting applications of 3D printing in medicine is the bioprinting, which involves printing the tissues and organs for transplantation and research purposes. Tissues and organs using bioinks can be made from living cells by bioprinting. It has a potential to produce organs for transplantation and addressing donor shortages. Here, let's delve into the advantages of combining these technologies. First, the customization. 3D printing allows us to create implants that are specifically tailored to the individual needs of each patient. Enhanced fit and functionality for better outcomes can be achieved. Second, the ability to produce complex geometries. Traditional manufacturing methods often fall short when it comes to complex designs. However, with 3D printing, we can fabricate structures that closely mimic the natural shapes and forms of biological tissues. Material efficiency is another key advantage of 3D printing. By 3D printing, they minimizes waste by using only the material needed to construct the implant, making the process more sustainable and cost-effective. Moreover, the technology enables rapid prototyping and production. This means we can quickly go from design to physical prototype, accelerating the development process and allowing for faster iterations and improvements. Lastly, the combination of 3D printing with advanced biomaterials results in improved integration and functionality of the implants. These materials can be engineered to enhance biocompatibility and mechanical properties, ensuring that the implants perform effectively within the body. The realm of 3D printable biomaterials, which play a crucial role in advancement of next-generation implants. The table on this slide categorizes these materials based on their utilization and findings, along with relevant references given here. Scaffolds for tissue engineering and regeneration are essential for supporting the growth of new tissues. For example, PCL and chitosan enhances cell retention and proliferation, leading to stronger osteogenesis and bone matrix with rabbit bone marrow mesenchymal stem cells. Additionally, PLA and biodegradable calcium phosphate increases cytokine production for IL-6 or IL-12 with human monocytes. For drug-delivery applications, polycaprolactone and estrogen receptor luciferase reporter cells enables patient-specific medicine and demonstrates bioactive retention. For surgical guides and implants, ABS is used for perioperative surgical simulation of conjoint twin separation, closely matching the CT data with mean deviation below 2 millimeters. This table here outlines different materials, highlighting their properties, applications, and limitations, along with relevant references. Starting with PLA, we see the properties such as being inexpensive, non-toxic, biocompatible, and biodegradable. The PLA is widely used for tissue engineering, scaffolds, and drug delivery. However, they exhibit mechanical weakness over time. Moving to polycaprolactone, we witness similar general characteristics with PLA. Next, polybutylene tetraphthalate. The PBT is a polyester thermoplastic, and it is primarily used for bone scaffolds. They also present mechanical weakness, and poor cell adhesion and bioactivity are notable drawbacks. If we have a look at the ABS material, this material is a three-block copolymer that derives toughness from strand units and strength from acrylonitrile and butadiene units. Their application is mainly limited to cartilage engineering only. ABS is a non-biodegradable material and it has a poor biocompatibility with a potential cytotoxicity. When we have a look at why mechanical properties are crucial for implants, we can say that for load-bearing applications, implants must support and distribute loads similar to natural tissues and bones. This ensures that the implant can function effectively without causing additional stress or damage to the surrounding tissues. Longevity and resistance to wear, fatigue, and corrosion are also critical for implant success. Durable implants reduce the need for frequent replacements and minimize complications over time. Additionally, implants should match the mechanical properties of surrounding tissues to prevent bone resorption and maintain the healthy bone density. This compatibility helps in preserving the natural biomechanical environment of the bone. By combining with advanced biomaterials, we can achieve these goals and develop implants that better integrate with the human body, enhancing both functionality and longevity. This table summarizes the general mechanical characteristics of various bone structures in human body. The mechanical features of metallic materials and 3D printable materials used for orthopedic aspects are also included in this table and the graph given below. These illustrations indicate that while metallic materials present superior mechanical characteristics over bone structures, 3D printable materials such as PLA, PCL exhibit very low elastic modulus, compression strength, and tensile strength compared to the bone tissues. By introducing reinforcement materials into a polymeric structure, their mechanical characteristics can be improved since the materials such as tantalum or hexagonal boron nitride microparticles exhibit the higher mechanical features as seen in this graph. In this part of this presentation, a case study on simulating the increased mechanical properties of 3D printable PLA and PCL by microparticle reinforcement is conducted. Here, a femur of an average human body who is 80 kilograms in weight is considered. As the average femoral diameter is about 3.2 centimeters, the compression value on the femoral bone and potential bone scaffold to be used in this part of the human body can be calculated as 24.5 Newton per centimeter squared, as seen in the image on the left side. This situation is created in SolidWorks by a model bone scaffold as seen here. The scaffold materials are selected as PLA, PCL, and femur individually. In addition, the same scaffold structures also remodeled by reinforcing the structure by hexagonal boron nitride microparticles as seen here. In this simulation, the stress and displacement amplitude on designed structures under given statical stress effects are analyzed individually. These tables summarize the input parameters of each structure in this simulation study and obtained results for each pure and reinforced structure. The table below and the graphs on the right side indicate that introducing hexagonal boron nitride microparticles into PLA and PCL improved the stress and significantly lowered the displacement amplitude, which resulting in a higher elastic modulus of the structure. Reinforcement in pure polymeric materials potentially makes the structure have similar mechanical features to bone structures, such as the femur here. The obtained results are also visualized by the image provided here. While pure PLA and PCL exhibit much more displacement amplitudes, as seen here, and lower stress values, microparticle reinforced PLA and PCL exhibit a similar result with femur structure, as seen in these three images. Now, if we continue with the role of 3D printing in creating patient-specific implants, we see how this technology is revolutionizing the medical field. 3D printing allows us to tailor implants to the unique anatomy and medical needs of each patient. By utilizing advanced imaging techniques such as computed tomography and magnetic resonance imaging, we can create highly detailed digital models of the patient's anatomy. These models are then integrated with CAD software to design implants that fit the patient's anatomical structures with very high precision. When implants are specifically designed to match patient's anatomy, they provide a superior fit. This results in increased comfort and more natural movement for the patient. Customized implants significantly reduce the need for intraoperative adjustments. This leads to shorter surgical procedures, which not only minimizes the patient's time under anesthesia, but also decreases the risk of complications that can arise during longer surgeries. Tailored implants designs promote better integration with the patient's tissues. This customization reduces the risk of rejection and infection, leading to a smoother post-operative recovery and better long-term outcomes. Personalized implants are specifically designed to meet the unique load-bearing and movement requirements of each patient. This optimization enhances the durability and functionality of implants, ensuring they perform effectively over a longer period. When we analyze the differences between traditional implants and 3D printed implants, highlighting the advancements and benefits that 3D printing brings to the field of medical implants. While traditional implants are typically manufactured in standard shapes and sizes, which may not perfectly match the unique anatomical structures of individual patients. 3D printed implants can be tailored to the exact anatomical structures of each patient. This customization allows for a precise fit and improved functionality, enhancing the overall patient experience. The manufacturing process for traditional implants offers limited customization. This lack of personalization can result in implants that do not fully meet the specific medical needs of patients. On the other hand, the layer-by-layer fabrication process of 3D printing enables the creation of complex internal geometries that are very difficult or impossible to achieve with traditional manufacturing methods. These intricate designs can significantly improve the mechanical performance of the implants. Traditional machining and casting processes can introduce internal defects and inconsistencies within the implant. These defects can compromise the mechanical integrity and performance of the implants over time. However, 3D printing offers the potential to integrate multiple materials into a single implant. This capability allows us to achieve a desired mechanical features and enhance the overall performance and biocompatibility of the implants. As we continue to explore the advancements in 3D printed materials, it's essential to also address the challenges and limitations we face in these innovative fields. One significant challenge is the limited availability of materials that are both biocompatible and suitable for 3D printing. While progress has been made, there is still a need for a broader range of materials that can meet the diverse requirements of medical implants. Developing materials that balance mechanical strength and biological compatibility is a complex task. The materials must be strong enough to perform their function while also being compatible with the body to avoid rejection and promote healing. About printing resolution, achieving with a resolution and precision in 3D printing, especially for complex structures, remains a significant challenge. Current technology struggles with producing fine details and smooth surfaces, which are critical for the functionality and integration of implants. The limitations in current 3D printing technology affect our ability to create intricate designs with the necessary precision. This can impact the effectiveness and comfort of the final implant. Furthermore, extensive post-processing is often required to enhance the surface finish of 3D printed implants and to remove residual stress that can compromise their integrity. This adds time and complexity to the manufacturing process. Additional steps are necessary to ensure the sterilization and biocompatibility of printed implants. These steps are crucial for patient safety, but also at the overall production time and cost. As we look ahead to the future of next-generation implants, we are at the cusp of exciting developments that promise to revolutionize the field. The first area to watch is the development of new biocompatible materials. Researchers are working to create materials that not only offer enhanced mechanical properties, but also provide superior biological functions. The integration of multi-material printing capabilities will allow us to combine various properties within a single implant, paving the way for more robust and versatile solutions. Next, we turn to innovations in printing technologies. The future will see significant advancements in improving the resolution, speed, and reliability of 3D printing. Additionally, hybrid manufacturing approaches that blend traditional methods with 3D printing will emerge, offering new possibilities for implant fabrication. Bioprinting is another groundbreaking frontier. We are advancing towards the creation of functional tissues and organs for transplantation using bioprinting technologies. The use of bioinks containing living cells and growth factors will enable us to print complex tissue structures, bringing us closer to the dream of organ regeneration. Smart biomaterials represent a fascinating development in the field. These materials can respond to physiological changes in body. For example, self-healing materials, drug-eluting implants, and materials that change properties in response to stimuli are the innovative designs that will enhance the performance and longevity of implants. Finally, the expansion of personalized medicine will revolutionize how we approach implants. Tailoring implants to individual patient genetics and physiology will become the norm. Utilizing patient-specific data, we can optimize implant design, placement, and post-operative care, ensuring the best possible outcomes for each patient. As we wrap up our discussion on next-generation implants, let's summarize the key points we have covered and look ahead to the future. The fusion of 3D printing technology with advanced biomaterials enables the creation of customized, high-performance implants tailored to specific patient needs, offering high precision and functionality. One of the significant advancements is the improvement in mechanical properties. Advanced biomaterials used in 3D printing enhance the strength, durability, and overall functionality of implants, making them comparable to or even exceeding the mechanical properties of natural tissues. This means more reliable and effective implants for patients. Personalization is another crucial benefit. Implants can be customized to fit the unique anatomy of each patient, which not only improves fit and comfort, but also leads to a better clinical outcomes. This tailored approach ensures that each implant meets the individual needs of the patient, leading to more successful treatments. Despite these advancements, there are still challenges to overcome. Technical, regulatory, and manufacturing hurdles need to be addressed to ensure the widespread adoption of these technologies. However, the future is bright with promising advancements on the horizon. In conclusion, the integration of 3D printing with advanced biomaterials holds great potential for transforming the field of medical implants. By addressing current challenges and continuing to innovate, we can look further to more personalized, effective, and high-performance solutions in the near future. So thank you for your attention, and I gave my details here. If you have any further questions or if you want to ask anything about this presentation of biomaterials field, you can directly send me an email or make a phone call, or you can also visit me in Turkey at my department as given the details here. Thank you again for your participation. I wish you all a peaceful and happy day. Goodbye.